No study of digital communications would be complete without addressing the issue of random processes. Now, random processes have a great deal of mathematical baggage, not all of which is necessary to understand in order to study digital communications. However, some of the basic concepts are important to understanding that you may not have seen in previous classes. Therefore, we'll take some time to go over the concepts that are most important for our study. So random processes are covered early on in the textbook from SCLAR, and in particular in sections 1.5, and this will be sufficient for our requirements. So in particular, we'll be talking about random signals of data. We'll discuss, first of all, what is the difference between a random variable and a random process, because I think everyone has already seen random variables. However, random processes you may or may not have come across. And so we'll start from the basis of what we know, random variables, do the expansion of random processes, and very quickly we're going to return back to treating random processes using the mathematics and the tools that you already know, those used for random variables. There will be a couple new ideas, new concepts that we'll bring about that you haven't seen before if you haven't seen random processes. And in particular, the ideas of stationarity and ergodicity are two principles that really come with random processes, and some of the assumptions on stationarity in particular will allow us to pass from random processes to a treatment of some of the same mathematics that you've already seen with random variables. So we'll see a few examples, some simple examples, so that I can help you appreciate a random process and how we would do manipulations with random processes. But very quickly we're going to move on to not really go further with random processes, but rather to focus on the idea of a power spectral density. So in the previous discussion, I talked about the energy spectral density for deterministic signals, the power spectral density for periodic symbols, and I said that random signals have a power spectral density. So talking about random processes, talking about stationarity, allows us to finally arrive at this concept of the power spectral density of a random process. So that's what we're going to do with random signals. Now, there's one other very important random process which hasn't to do with our signals, but rather has to do with noise. And additive white Gaussian noise in particular can be modeled very easily as a random process. So that will be the last topic we cover in random processes. So random variables. I said random variables is a concept you've probably seen. And you know that there is a distribution function, which we usually use capital F, with the subscript of capital X and an argument of small x. Okay, so there are some nuances to the use of this very standard notation. The small x is just a number. The capital X means a random variable that takes values which are numbers. So the little x, the lowercase x, is the number it takes as a value. And of course the capital F of x is this distribution function. Closely related to that is the probability density function, which we use a lowercase f. And again, we have the index of capital X because the probability density function will vary from one random variable to another. You can have a random variable which has a Gaussian density. You can have another random variable which has a chi-square density. We'll give a name to each one, and then we'll use this index to indicate which one we're referring to. For instance, x is Gaussian, y is chi-squared, and we'll have f of x or f of y, etc. Now, there's one operation which we see very, very often when we deal with random variables, and that is the expected value of a random variable. And the notation we use for an expected value is the operator capital E before the random variable. And the definition of the random variable is sort of the average value of the variable. So how do we find the average or the mean or the expectation? All of these are synonyms that we sometimes see. Well, we take the probability distribution and we average the value across this distribution. So we have an integral from minus infinity to infinity, and we take the value that this random process takes, that's the small x. Each value of x has a weight with its probability, and then we take the integral across dx. So I'm sure you've seen all this. This is just a little review and a presentation of the notation that I'll be using to discuss random variables and random processes. So let's talk about random processes. How is that different from a random variable? Well, first of all, it's a function of time. So process means varying with time. So here I have capital X of t. Capital X of t represents my random process. Little x of t, and in here I have an index of 1. That means one realization of the random process. So when we talk about stochastic theory or about random variables, we often talk about having a hat, and in this hat we reach in and we pull out the value that it takes. So this hat represents the randomness, the stochastic nature of the random variable that we're doing. So when I reach in my hand and I pull out a random variable, essentially I'm pulling out a number. And each time I put my hand in and I pull out, I've got a different number, a different realization. So I'm taking a sample and it's giving me a realization. So the index here is telling me which realization, because when I have a random process, I reach my hand in that hat and I pull it out and I have a complete function of time. So that's what is described here. I have a random process, I reach in the hat, I pull it out once, that first one is first realization. And of course, each time I reach in the hat, I get a different realization. So for instance, here's a list of 4 realizations that I have for what is the same random process. This is just each time a random sample. And sometimes we talk about having a sampling space, and reaching in the hat is this finding a sample. And then there's this correspondence between, well, a sample gives me a time function. So some books will use a notation something like this, where we have a sample space. We realize we pick something out of the sample space, and that sample space for a given random process, well, it yields a function of time. Okay, so depending on your background in random variables, maybe this is something that you've seen before. But the important concept is the randomness applies now to a function of time. So now let's talk about this connection between random variables and random processes. It's very important, this connection, because we have a whole lot of knowledge and background on random variables that we would like to bring to bear and use them with random processes. So how do we do that? Well, we take a random process, x of t, and we define a variable which is the precise value of this function of time at a given instant of time. So if I pick an instant of time, tk, then the value of that random process at that instant of time, well, that's one value. At an instant of time, it's one value. It's not a function of time anymore. It's the value at one point of time. And therefore, now I've got myself a random variable. So if each of these is a different realization of the process x of t, then if I think of the time tk, pardon me, at the time t equal k, well, each one of these values becomes the realization of this random variable. So remember, I pulled in my hat, I pick out one sample, and it gives me this realization, but it also indicates that at this time tk, it's one realization of a random variable. Okay, so if I sample the random process, I get a random variable, and that's something I can deal with easily. Now, that sounds easy. I can go from random process to random variable, but of course there's something a little more complicated. And let's make this easy. And again, you've probably seen these ideas that I'm going to discuss now, again, in your study of random variables. But now I'm going to address these ideas in the view of having a random process. But let's say I take a random process and I sample it at 2 different times. I sample it at time equal 1, and I sample it 1 second and time equal 2 seconds. So now I have 2 random variables. Okay, so think back to your class on random variables when you have 2 random variables. Well, when you have that, there may be some correlations between these variables. They may not be completely independent. In fact, the fact that I have one value versus another could influence. For instance, a very easy example is age and height. If you go into a grade school and you sample people and you have one variable is their age, the other value is the height, while when their age is really young, they're probably going to have a lower height. When they're older, they're probably going to have a larger height. So these are two examples of random variables which are highly correlated. So how do we deal with that? Well, one thing we can do is we can do something called a scatter plot. And a scatter plot lets us visualize what might be going on. So it's like the easiest way to look at this concept of two variables. So here we have plotted x and y, and each one of these dots represents for a given sample. We reach in the hat once, we pull out a sample, and we look at what was the value of x and what was the value of y for this sample, and that becomes a point in this space. And we can see that if we do 4 different systems described by a different random process, 2 samples at a different random process, I can get very, very different behavior, very different kinds of correlations between them. For instance, if I look at the first one here, I don't really see much correlation going on. It seems pretty uniform. So maybe these x and y are not correlated at all. Maybe they are completely independent of one another. Now we see this one, which looks a little bit like that idea of age and height. When the age is low, the height is probably low, etc. So this might be one with some very traditional correlation, linear correlation. Then we have some others here which are circular, looks more circular. However, there's some that seem to more dense, a little more tightly packed, some less tightly packed. The idea here is it can be like all kinds of different behavior. Just 2 variables and already there's something complicated going on here. For one thing, the way that I would describe this is a scatter plot for visualizing, but I can also define a 2-dimensional probability density function. So for a single variable, I have a PDF, a probability density function, but if I have 2 variables, I have to do it jointly. And so now I look at what's the probability of the ordered pair x and y, and now I have this contour that gives me the probability of the ordered pair. So it's a probability density function with 2 arguments now. And it's the joint PDF because it takes account of both x and y jointly, so I know how they're interacting in particular. You can see that this looks something like a Gaussian, and if I take cuts in different directions, I'm going to get what we call a marginal density. For instance, if I take a specific value of x and I go across and make a cut, I might get a nice Gaussian distribution. And that would be the marginal density. If I forget about y, I just walk into that grade school and I just measure everybody's height and I look at the distribution of it, maybe it'll look like that. Maybe that's a poor example. Maybe it's not height. If I go into the 3rd grade and just have the height of the 3rd graders, maybe it would look like a Gaussian distribution. So that's a marginal density. I take the joint density, I take a specific value, and then I look at how the other variable, so if I take a specific value of x, for instance, I look at what the distribution is in y, etc. So that's a marginal density. So going back to this example of different random processes, at any instant of time, I have a particular PDF. I have a PDF that describes the random variable, which is this random process sampled at time tk. But this random processes, for instance, could be Gaussian at this point, and it's possible that if I take another instant of time, it could be a Ricean or a Rayleigh distribution. It could look completely different. So knowing the marginal density for one instant of time doesn't tell me anything about the joint density. It doesn't even tell me anything about the marginal density at another instant of time. So in order to describe the random process, if I really want to know what's going on with the random process, well, suppose that I knew the marginal PDF at every instant of time, not just 2, but suppose I knew it at all. And that's already complicated, right? Because it's a function of all time. I'm looking at an infinite number of marginal PDFs, and you think, okay, now I know about this random process. No way, you don't know much about it at all. Knowing the marginals is not enough. What you have to know is the joint distribution. The joint distribution, we saw that with just 2 random variables. Now imagine the difficulty of knowing everything about a random process an arbitrary random process, because then I'd have to use the joint distribution function for an arbitrary number of samples. So if I knew the joint distribution if I sample any different 5 samples, well, that would be a function of 5 variables, but that's still not everything. I have to know for 6 variables, for 7 variables. So you need a whole lot of information to know about the complete stochastic nature of a random process. So that's why I say the mathematical baggage that goes with random processes can be very complex. Of course, we don't treat the arbitrary random process. What we're going to do is we're going to look at subsets of random processes which have characteristics that reflect nature, reflects the systems that we're going to be examining, and that also makes the mathematical description of these random processes much simpler. So I scared you a little bit telling you about how complex random processes can be, but now that I've done that, I'm going to step back and start looking at kinds of random processes that are important to us, have very high structure, and that are going to make them much easier to deal with. So in summary, random processes, well, first of all, they're random, so we're talking about probability density functions. It's a process, so it's a function of time, and there are all kinds of correlations, so that means that I need joint PDFs, and as I mentioned, this could be extremely complex. So I said we're going to simplify it. So how are we going to simplify it? We're going to simplify it by looking at only 2 moments of this function of time. Moments, of course, are expectations of different orders of the random variables when we talk about random variables. So in this case, we're going to be talking about expectation. We're going to talk about the mean, and we're going to take the mean of the autocorrelation function. And that's going to be one of the moments that we're interested in. So we saw autocorrelation function already in our discussion of the spectral densities. And so it's not surprising that when I attack random processes, because I say to you, I want to find the power spectral density, that I would pass via the autocorrelation function. So again, we're going to have to simplify it. Even calculating the mean of the autocorrelation function can be difficult. I'm going to show you how to do that next. So when we do this calculation of the mean of the autocorrelation function, we also have to reduce it to a certain class of random processes for which the calculation is easier. And so we're going to be looking in particular at a subset of random processes which have the property of being wide sense stationary. And the acronym we use is WSS. And so often it's the first assumption you make in a communication system that the random processes you're dealing with are wide sense stationary. So what does this mean, wide sense stationary? Well, in order to give you even the definition of wide sense stationary, I have to give you a few more definitions of moments of random processes. So let's start with the easiest one, which is the mean. What is the mean, the stochastic mean of a random process? So I'm going to use the notation here, ux of t. So mu here is going to be the symbol I use for mean, or the expectation. So by definition, it's the expectation of the random process. And of course, since x is a function of time, then the mean also will be a function of time. So by definition, I take the value and I average it over the PDF, and this is the PDF of a function at a specific instant of time. So what have I done here? I have made the calculation. What it requires is the marginal density at one instant of time. So at one instant of time, like here, I have time 1 here. So at time 1, these are all realizations of the random variable, which is x at time t1, capital X at time t1. Capital X at time t1 is a random process, right? And so if it's a random process, I have to find its expected value. So then I write ux of t1, and that is just minus infinity of x of t1. And now I average it over this is like lowercase x. This is capital X of t1. So this is f of lowercase x of t1, dx of t1. So I've taken an instant of time. So this is one value of t1. This is one value of t1, one value of time. That gives me a random process. X of t1 is the random process. It has a certain marginal distribution, a certain PDF. And now I take that PDF, who's got an argument which is a real number, and I weight that real number by this density, and I take the average from minus infinity to infinity. Okay, so that means that at this instant of time, I get one number. You know, I do this integral, it gives me a number. That number is the mean at this time. So I do that again at each sample of time. So now I have a different mean and a different mean. So this means that the mean of a random process is in general a function of time. So I now understand how to calculate the mean of a function. But I said that I was going to take the expectation of the autocorrelation function. So now I have to start thinking about what is the autocorrelation function for a random process. So let's think a little bit about what the autocorrelation function is trying to, how we're going to exploit it. What's it's going to help? What kind of questions is it going to help us answer? Well, for instance, here is a realization, one realization of a random variable. And I can imagine different instants of time. And I can time 1 second, time 2, 1.3 seconds, whatever, different values of time. And I wonder how similar are these two values of time? If these are nearby to one another, are they more likely to be, like close to one another? If they're farther apart, are they less likely to be like the same value? Suppose that it's Monday at 3 o'clock in the afternoon, and this is the next Monday at 3 o'clock in the afternoon. Does that matter? Is there like some periodicity to it? What's going on? I don't know. So when I look at autocorrelation, this is a tool for me to start answering some of these questions about how related are values of this realization at different points in time. So we'll try and make it simpler. I'm not going to just do an arbitrary number. Suppose I just take 2 samples. And I just ask these 2 samples, how much are they similar to one another? And how much are they similar? I'm going to call that the autocorrelation function. Because of course I could name different functions, but the one that interests me is the autocorrelation function. So by definition, if I take 2 samples, one at time t1, one at time t2, I'm going to define the autocorrelation function, which right now is a function of 2 variables, time 1, time 2. By definition, it's the expected value of the product of the random process at time t1 times the random process sampled at time t2. So what is the expected value? Well, I know that I have to do a double integral because I have 2 random variables, and I take each one of the random variables, multiply them together, and now I have to average them. But when I average them, I'm averaging them over here over the joint PDF. So that's what we see going on here, is f of not the marginal of x1 and the marginal of x2. No. It's the joint PDF of both of them. So here I have an argument of both. So this is remember, like this 2-dimensional plot of the probability density function for an ordered pair x1, x2. What's the probability of that ordered pair? So this is the double integral, and it's over the joint density function. And because here I've just defined 2 samples for the function. So the autocorrelation function, as I've defined it now, I have 2 variables. So before I was saying sampling it at all kinds of different times, now I'm looking at 2 variables, and I'm going to give you a suggestion on what would be a good way to interpret what's going on when I have 2 variables. So suppose that I think of a certain separation in time. Like if things are 1 second apart. Here's 1 second apart on Monday. This is 1 second apart on Tuesday. This is 1 second apart on Friday. Okay, so you can think of it as being the same lag The lag here is the same, but the absolute position in time could change. Okay, so this is a situation that is a little different from saying, pick 2 samples anytime. Suppose I restrict my attention to picking 2 samples so that they're also always the same distance apart. Well, in this case, it could be a function of one variable. Suppose it didn't matter whether it was Monday or Tuesday or Friday, and it didn't matter if it was Monday morning or Monday afternoon. The only thing that mattered in the result from my autocorrelation function was how far apart they were. Because if they were really close together, they were maybe highly correlated. It didn't matter what day it was. But if they're really far apart, maybe they're not very correlated at all, and it doesn't matter where I am in the timeline. So I could be like 3 years ago, but they were, a week apart, there would be no correlation. And now 10 years from now, but they're a week apart, there's no correlation. So you can see there's these 2 ideas of time. One is the lag, the distance between my 2 samples, and the other one is the absolute position in time. So this is going to be the concepts that we're going to use when we talk about wide stationary. So I'm getting closer and closer to that. By the way, I'm going to use tau to represent this idea of a lag between 2 functions, two time instants.